professor at LJ Institute of Engineering and Technology. Today we are going to study few more topics of system of linear equations and matrices. So let's begin with the first topic, that is diagonalization of a matrix. Let A be a square matrix of order n. Okay, so the matrix A is said to be diagonalizable if there exists a non-singular matrix P such that P inverse AP equals to D, where D is known as diagonal matrix and P is known as modal matrix. Okay, so firstly we are taking a square matrix of order n. Okay, and when we can say that this matrix is diagonalizable if we have this non-singular matrix P. Non-singular means what? Determinant of this P should not be equal to 0, right? So we have this non-singular matrix P such that P inverse A into P, this is equals to D, and where D is what? It is a diagonal matrix, right? Now an n cross n matrix is diagonalizable if and only if it has n linearly independent eigenvectors. Okay, so when we can say that n cross n matrix is diagonalizable if we have n linearly independent eigenvectors. So for example, if we have 3 cross 3 matrix, then we should have 3 linearly independent eigenvectors. Then we can directly say that this 3 cross 3 matrix is diagonalizable. Okay. Now, let's study the working rule for diagonalization of a square matrix. So the first point is find the eigenvalues of a square matrix A. Okay, so firstly we will find the eigenvalues from characteristic equation. Okay, next we will find the eigenvectors corresponding to each eigenvalue using the formula, that is A minus lambda I into x equals to 0. Okay, we will use this and we will find eigenvectors corresponding to each eigenvalue. Next we will find modal matrix P by writing the eigenvector as its column vector. Okay, so we will write this matrix P by writing the eigenvectors in the column form. Okay, next we will find this P inverse AP, and this will be equals to D, where D is what? D is a diagonal matrix and which has eigenvalues as its diagonal elements. Okay, so in this diagonal matrix here we have only elements present at this diagonal. Okay, and these elements are eigenvalues of that matrix. Okay, now let's study one example. Find a matrix P that diagonalizes A and determine P inverse AP, where A is given, that is 2 0 minus 2 0 3 0 and 0 0 3. So let's begin with the solution. Here matrix A is given, that is 2 0 minus 2 0 3 0 and 0 0 3. So firstly we can see that this matrix is upper triangular matrix, right? We have a triangle form here. So this is upper triangular matrix. Now we have this property that if we have upper triangular matrix, so the eigenvalues will be its principal diagonal elements. Okay, so the principal diagonal elements are 2 3 3. So the eigenvalues of this matrix is what? 2 3 3. Okay, now we will find eigenvectors corresponding to these eigenvalues. So firstly we will find eigenvectors for lambda equals to 2. Okay, so we'll use the formula A minus lambda I into x equal to 0. Okay, now we know this matrix A. This is what? 2 0 minus 2 0 3 0 and 0 0 3. Okay, so firstly we will find this A minus lambda I. Here lambda is 2, so we will write 2 into identity matrix, that is 1 0 0 0 1 0 0 0 1. Subtract this 2. So if you firstly will multiply 2 here, right, so you will get 2 everywhere, and if you will subtract it, so you will get changes at this principal diagonal elements. Okay, so here 2 minus 2 will give 0, then 3 minus 2 will give you 1, and 3 minus 2, so 1. All other elements will remain same because here we have 0, right? Now we will write the equation from this. So you will get here 0 into x, so 0x plus 0y minus 2z. So we will just write this minus 2z is equal to 0. From this second row we will get y is equal to 0, and this from third we will get z is equal to 0. Okay, now we have the value of y and z, that is 0, but we don't have the value of x. So what we will do, will suppose x. Okay, so let's suppose x is equal to t1, where t1 belongs to r. Okay, so you will get the vector x as x, y, z. Just substitute the answer of x, that is t1. We know y and z are 0, so write down here 0. Okay, now we'll take t1 common from this, so you will get t1 into 1, 0, 0. Okay, now we will write this as x1, so we have t1 x1, where x1 is what? x1 is eigenvector corresponding to lambda equals to 2, right? Now we will find the eigenvector for lambda is equal to 3. Okay, so again we'll use this formula, that is a minus lambda I into x equal to 0. Okay, so now we know this matrix A is what? 2, 0, minus 2, 0, 3, 0 and 0, 0, 3. Okay, next minus, here lambda is 3, so 3 into 1, 0, 0, 0, 1, 0 and 0, 0, 1. Multiply 3 inside, so you will get 3 at these 3 places. Subtract it, so what you will get here? 2 minus 3, so you will get minus 1 here, then 3 minus 3, so 0, and again 3 minus 3, so 0. All other terms will remain as it is, right? Now this 2 are 0, so we'll get only one equation from this first row, that is minus x minus 2z is equal to 0. Okay, now we will take minus common from this, so you will get x plus 2z is equal to 0. Okay, and we will suppose this y as t2 and z as t3. Okay, so you will get the answer of x as, bring this 2z here, so you will get x is equal to minus 2z, and z we have supposed as t3, so it is minus 2t3. Okay, now we will find this x, that is x, y, z. Now in place of x we will write this minus 2t3, in place of y t2, and in place of z t3. Now here we have t2 and t3 together, so firstly we will split them. Okay, so here we don't have t2, so here it will come 0. Here we have t2, so we'll write t2. Here we don't have, so we'll write 0. Plus, now here we have, so we'll write minus 2 t3. Here we don't have t3, so we'll write 0, and here we will write t3. Okay, now we will take t2 common from this and t3 common from this. So from here you will get 0, 1, 0, and if you will take t3 common from this, you will get minus 2, 0, 1. Okay, now we'll suppose this as x2 and this as x3. Okay, where x2 and x3 are eigenvectors corresponding to lambda equals to 3. Okay, now we will write this model matrix P, okay, which has eigenvectors as its column vector. So P is equal to what? This is the eigenvector for lambda is equal to 2. Okay, this is the eigenvector for lambda equals to 2. And the eigenvectors for lambda equals to 3 are this 2. So we have to write it in the column form. Okay, now we have to find this P inverse. Okay, so for that we will apply Gauss-Jordan method. So for that what we need, this P is equal to I3P. I3 means it is an identity matrix for 3 cross 3. Okay, now just substitute the value of P and I3. Okay, so P is this, so just substitute it. I3 is 1, 0, 0, 0, 1, 0 and 0, 0, 1. P we will keep as it is. Okay, now we know the procedure to find the inverse. What we have to do, we have to convert this P to I. Okay, and on conversion we will get here a new matrix. Okay, and this new matrix will be your inverse. So here we have to make a identity matrix, but for that we need only 0 at this places. Okay, so you will get directly I, that is identity matrix. Okay, so we will use the row operation as R1 plus 2 R3 and we'll make changes in R1. So you will get here 1, 0, 0, and this 2 row will remain as it is, and here we will get 1, 0, 2, and this 2 row will remain as it is. Okay, So here we have I and here we have a new matrix. So we will write as I3 is equal to P inverse P. Okay, so this is your P inverse. So we'll get the answer of P inverse as 1 0 2 0 1 0 and 0 0 1. Okay, now the next step is to find this P inverse AP. Substitute the answer of P inverse, this A and P. If you will multiply this 3, so you will get this matrix, and this matrix is a diagonal matrix. Okay, and the elements of this principal diagonal are the eigenvalues. We know the eigenvalues, that is 2, 3 and 3. Okay, so this is our diagonal matrix which we obtained by P inverse AP. Okay, so in today's session what we have studied, diagonalization. Okay, so when we can say that a matrix is diagonalizable, if we have a matrix P which should be non-singular. Okay, and this P inverse AP, it should be D, and D is what? D is a diagonal matrix, right? This P is known as a model matrix. Okay, now what is the procedure? So firstly we will find the eigenvalues, right, using the characteristic equation. Okay, and then we will find eigenvectors using which formula? This A minus lambda I into x equal to 0. Okay, so we will get eigenvectors corresponding to each eigenvalues. And the third step is to find model matrix P, and this we will get used by substituting the eigenvectors in the column form. Okay, and next we will find P inverse, and then we will find this P inverse AP. So you will get D. Okay, so this D is what? This is a diagonal matrix, and the elements of this diagonal will be the eigenvalues. Okay, so I hope you have understood throughout the session. Thank you for watching.